Welcome to SCA's broadcast today on production forecasting. I'm Susan Howes. I'm with SCA, and we're starting our webinar. We welcome today Dr. John Lee. He'll be giving us a webinar on identifying flow regimes, a big assist for production forecasting. Dr. Lee is a professor at Texas A&M. His education is from Georgia Tech. He started his career at ExxonMobil. But most of his career has been in academia. He's been the Regents Professor at Texas A&M in Petroleum Engineering. He also did consulting for Holditch and Associates, and he served as an academic engineering fellow with the SEC when they modernized the SEC rules for reporting oil and gas reserves. Recently, he's been serving at University of Houston as the Cullen Distinguished University Chair. He's authored 4 textbooks published by SPE. He's the winner of the Lucas Award, the DeGoyer Medal, and honorary membership for SPE. He's a member of both the National Academy of Engineering in the United States and the Russian Academy of Natural Sciences. So this is a sample of John's class that he offers through SCA on production forecasting for low permeability reservoirs. This class is scheduled in a public venue in Houston in both January and May. And it's a 2-day class, and you can see the outline of the contents of the class there. It's also on SCA's website. And if you need any more information, or if you would like to schedule a private training class in-house, please contact SCA. So at this point, SCA is a consulting firm. We also provide direct hire services. We do projects and studies, and of course training. And it's my pleasure to introduce to you Dr. John Lee. John, I'm going to pass over presenting rights to you, and then we'll get started here.
All right. Thank you, Susan. Good day, everyone. Thank you for joining us in this webinar. As Susan has told you, what I'm going to be talking about today is a topic which is a subset of the 2-day course that we will be offering later in January and then in May. And this specific topic from the course is on identifying flow regimes, which is a big assist for production forecasting. Well, let's start with some background on this topic and ask the question, what's the problem that we're addressing? Well, the problem is that production forecasts provide the basis for reserves estimates, but without some sort of control on forecasting methods, those forecasts can be from somewhat to very inaccurate. And of course, inaccurate forecast means inaccurate property valuations, inaccurate reserves reporting. So, the solution to this problem is in decline curve analysis, which is really going to be our focus today. We can make use of industry findings which have been developing pretty rapidly in recent years on elements of forecasting which are known to improve the accuracy of the forecasts, specifically identifying distinct flow regimes in production data, including early transient flow, that is flow unaffected by reservoir boundaries, and then boundary influenced or boundary dominated flow, that is flow in which we have begun to drain from the entire drainage area of our well. All right, the next step then is to find parameters in our decline models. Most people use the Arps Hyperbolic decline model, so that's what we'll discuss here today. But we need to find those parameters separately for each flow regime rather than try to fit all the available data with a single model. When we have difficulty in identifying where we are, it is important to weight the most recent data and therefore the most recent flow regime most heavily in our analysis. Now, if we're in a certain flow regime, but we expect future flow regime changes to occur, then in our modeling work, we need to include the timing and appropriate decline models in our forecast. And we need to ensure that whatever decline curve analysis software is used, that it allows us to incorporate these elements. The benefits of doing this: more accurate forecasts, better assessments of property values, more accurate inventories of reserves and other resources. So let's begin to look at our flow regime, starting with one which is almost always present in horizontal wells with multiple stages of hydraulic fractures. This is the dominant way that we're now drilling and completing in our resource plays. All right, this linear flow regime, I want to illustrate quickly here with a schematic showing a well with a hydraulic fracture associated with that well. The well and the hydraulic fracture. All right, if the conductivity of that fracture is large enough so that there's negligible pressure drop from the tip of the fracture to the wellbore, then the flow pattern that will develop will be transient linear flow and will begin to drain further and further out into the formation away from the fracture with increasing time. And that linear flow regime will continue in our horizontal wells with multiple fractures until we get interference between different stages of fractures in our well. We almost always see this flow regime. The only time that we wouldn't would ordinarily be when there's been some sort of failure in the fracture treatment itself. But in the many hundreds of wells that I've looked at from these resource plays, I almost always see this flow regime. All right, fluid flow analysts have shown us that that there's some fairly simple looking mathematical models which can describe this transient flow regime. And the general form of the model, and it's general in that it works for varying rate and also varying pressure drawdown. Now, in the special case where the pressure drawdown is constant, this delta P can be moved to the other side of the equation. It'll still retain the same form. But in general, the ratio of drawdown to rate instantaneously is proportional to the square root of time. And M sub L, that's just a constant of proportionality. One item that's often neglected in discussing this flow regime is the possibility of fracture skin. This is damage within or around the fracture itself. We don't want to assume that this is negligible unless the field evidence indicates that it is. And existence of this term will have an influence on the shape of the plots that we use to identify flow regimes. All right, when the data, the field data that we work with to analyze and to try to find our flow regimes is sufficiently free of noise, we may be able to calculate derivatives of this pressure drop divided by rate. And when we do, that gets rid of the fracture skin. All right, now let's talk about what would happen with plots of the derivative or the drawdown divided by rate on a log-log plot. First, the derivative. If we take the log of the derivative and plot it versus the log of time, this equation says we should expect a straight line with a slope of 1/2. That's how we can identify transient linear flow. If the data are so noisy that we really can't calculate derivatives with constant, then we have to resort to a log-log plot of delta P over Q versus the log of the sum of these two terms, not just, it involves more than just the time term. Eventually, the time term will become large compared to the skin term, but that takes some time. So if we're trying to identify the flow regime for the half slope, we can do that much more definitively with the derivatives if we're able to calculate derivatives. If we can't, we have to use a log-log plot of delta P over Q versus time, but there will be a delay in general in seeing the start of that straight line. So here's what a diagnostic plot would look like for transient linear flow. A diagnostic plot, that's simply a log-log plot of the variable in question, either delta P over Q or the derivative versus time. With the derivative, if we have transient linear flow, we'll always see a straight line with a slope of 1/2. That means over 2 log cycles every time we go up 1. If there is no fracture damage, we'll also see a straight line on the log-log plot of delta P over Q versus time, same half slope. But if there is fracture damage, which again in my experience is usually the case, we won't see that half slope immediately. Instead, our curve will be asymptotic to that half slope and only approach it at later times, as illustrated in this diagram. So if we're fortunate, we're able to calculate derivatives and use that as the basis for our diagnostic plot. All right, the second flow regime that's important for us to discuss is what I call the volumetric flow regime. The example that I want to illustrate of this flow regime is pseudo-steady state flow. And I give you a very detailed equation here. Let's don't worry about the details. Basically, this equation says that pressure drawdown is proportional to time during pseudo-steady state flow. All right, the general form of this equation then is drawdown is proportional to time, and there's an intercept. And in this case, we can't get rid of that intercept. It's always going to be there. Not just a matter of a fracture skin, which may or may not be present. All right, the derivative does get rid of the intercept. And again, let's think about a log-log plot of derivative versus time. In the volumetric flow regime, we expect to see a straight line with a slope of unity. Log derivative is equal to log of constant plus log of time. The slope is the multiplier on the log of time term. That's unity. If we can't get derivatives, then our log-log plot will simply be of drawdown versus time, but we'll be delayed in seeing the unit slope line until the time term becomes large compared to the intercept. So here's what the log-log diagnostic plot will look like in this case when we're trying to identify volumetric flow. The unit slope line over 1 log cycle every time we go up 1 log cycle. That's the characteristic signature of this volumetric flow regime. That was the derivative. This is the drawdown. The drawdown, again, will be asymptotic to the unit slope line. Now, for both the flow regimes that I've shown you, we have slopes of 1/2 for linear flow and 1 for volumetric flow, respectively. Some people prefer to plot instead of delta P over Q, they prefer to plot Q over delta P. That still works. The result will be slope of -1/2 for linear flow and -1 for volumetric flow. And in most of the examples that we're going to be showing later, actually, that's the kind of plot that we'll be looking at. All right, one more item in our background as we begin to move towards some examples illustrating how these ideas work. But an important additional item is the use of material balance time in our quest to identify flow regimes. Now, the definition of material balance time is material balance time, T sub mv, is cumulative production divided by rate. N sub P, that's the symbol for cumulative production of oil. G sub P, cumulative production of gas. Material balance time works either way. I want to introduce a couple of definitions for you because they're necessary in understanding a couple of slides that follow. QD, that's the symbol that we use to a solution to the flow equations for production at constant bottom hole pressure. And notice the quantities that are in this definition: rate, volume factor, viscosity, permeability, thickness product, and pressure drawdown. All right, this solution assumes constant bottom hole pressure production, variable rate. Another solution to the flow equations that we can find is a solution for constant rate production. And we use the symbol P sub D for that solution. Notice that the reciprocal of P sub D has exactly the same form as the solution for constant bottom hole pressure. That is, the same terms are here. Of course, there's a difference in the quantities within these definitions. For constant bottom hole pressure production, delta P is constant and rate will be decreasing with time. For constant rate production, rate is constant and pressure drawdown will be increasing with time. Well, what does this have to do with material balance time? What we'll see on the next couple of slides is that if we plot Q over delta P from a long-term production period for a well of interest, if we plot that versus material balance time, that will not change the shape of the curve during transient radial flow or transient linear flow. In other words, a log-log plot of Q over delta P versus ordinary time, or a plot of Q over delta P versus material balance time, will have the same shape of the curve on that plot in both cases. However, when the well gets to boundary dominated flow, when it achieves this volumetric flow regime that I described earlier, if we plot versus material balance time, that will change the shape of the Q over delta P plot on the material balance time plot, and it will cause the shape to be the same as the shape for constant rate production. That is, we will get a unit slope line during boundary dominated flow. Now, I realize that all this is just words. We really need to see some graphs to understand what I'm driving at. So, look at a couple of figures with you. Here is a plot of dimensionless rate, that's constant bottom hole pressure production, or reciprocal of dimensionless pressure, that's constant rate production, versus time. Now, at earliest times on this plot, the constant rate solution, which is shown in blue, differs slightly from the constant pressure solution, which is shown in red. But after what really amounts to a short period of time, you really can't tell the difference in these solutions on the plot. On a scale like this, the curves basically overlay each other. However, when we begin to feel the influence of boundaries, the plot for the constant rate production will quickly assume this negative unit slope, indicating that we're in boundary-dominated flow. For the constant pressure solution, the curve becomes much steeper and begins to fall off as illustrated here. Now, it is difficult to identify on the red plot the constant bottom hole pressure case. It's difficult to identify the point at which the flow actually achieved full boundary dominated flow. We can see when we get a departure from transient flow here, and we have a transition region, and for constant rate production, we can see eventually that we will reach this negative unit slope line. And so we'll know when we're in the boundary dominated flow regime. But for the constant pressure solution, we can't tell when we got to complete boundary dominated flow. We know the transition region began here, but all we know is the slope is steepening and steepening and steepening some more. We really need to be able to find the true start of boundary dominated flow, and we can't with a plot of field data, Q over delta P, or just Q if bottom hole pressure is constant versus time. However, if we make the plot of QD or reciprocal PD versus material balance time, look what happens. During the transient region, we still can't see the difference in constant rate production and constant bottom hole pressure production solutions. The solutions coincide. But look what happens when we get to boundary dominated flow. Plotting versus material balance time changes the shape of the curve for constant bottom hole pressure production, and it becomes identical to the curve for constant rate production. This gives us the opportunity to identify the true start of boundary dominated flow. Now, what's this boundary dominated flow going to be in our horizontal wells with multiple fractures? It's going to occur when we get interference between adjacent fractures. Now, if the fractures aren't exactly equally spaced, if the conditions are not ideal, we may have a bit longer transition period between the end of transient flow and the start of boundary dominated flow than shown on this graph. Nevertheless, we will, in most cases, see a true beginning of boundary dominated flow from this unit slope line on a log-log plot. So here are our conclusions from use of material balance time. For a well producing with variable rate, generally, this includes the special case of production at constant bottom hole pressure. On a plot of Q over delta P versus material balance time, we can identify transient linear flow with a straight line with a slope of -1/2, and we can identify boundary dominated flow with a straight line with a slope of -1. Now, one other item about flow regimes before we begin to look at some examples. In addition to the expectation of seeing transient linear flow for these fractured wells and eventually boundary dominated flow when we get fracture interference, there's some other things that happen at early times. And we need to take these other things into account when we're trying to analyze production histories to prepare ourselves for finding parameters in decline models for production forecasting. And this is illustrated on this graph, which I've taken from a paper by An Duong. If you want to look up the paper, I've given you the reference number on the slide. This is a log-log plot of rate versus time. These are data from a well in the Barnett Shale. And the red dots shown on this graph, these are measured rates for this well. Notice that we have an increasing rate at some early times, then sort of a flat rate for a while, and only until we get to 60 or 70 days in the history of this well do the data begin to fall on a sustained trend. And this trend can be fit very well by a straight line with a slope of -1/2. We go over 2 log cycles every time we go down 1. So in this example, we have a clear case of transient linear flow. And although the data get pretty noisy at the end, we can still argue that this trend continues up to the end of history that we have, about 2,000 days. But the early data are off trend. And I want to emphasize that. If we're trying to find parameters in a decline model for forecasting future production, we wouldn't want to include these off-trend data. We need to identify what appears to be the start of transient linear flow and analyze data throughout that flow regime in determining our decline parameters for this section of the production history. Eventually, we're going to see boundary-dominated flow, and we'll get a bend away from this trend downward, as I illustrated earlier, but we haven't seen that yet in this case. Here, there's more information than just those measured rates on this graph, obviously. The yellow, these are measured wellhead pressures. And what we can see here is that this well has been choked back. The pressure starts out fairly high. The pressure scale is over here in SI units. The pressure comes down and really doesn't reach a plateau or stable level until 70 or 80 days. You know, it's a judgment call as to when we can say the bottom hole pressure is finally settled down. Still a lot of noise in that data, but it does settle down eventually. The black dots that are shown on this graph are rates that have been corrected to what they would have been had the pressure been at this level during the entire well history. And the interesting thing happens there. These corrected data fall on the same straight line with a slope of -1/2 all the way back to something like 15 days. Before that, pressure correction didn't cause the data to come back to our straight line. So Duong said in his paper, from which I've taken this graph, the explanation for the difference between the observed rates and these pressure corrected rates, that's a combination of what he calls skin effect and surface choking. And we can see the surface choking with this pressure history. We can correct for that. We could correct for that if we have pressure measurements. And of course, we don't always have those pressure measurements, but if we do, we could correct for it. However, if we're analyzing data from dozens, hundreds of wells, most of the time we don't have time to do that. We just have to accept the measured rates and identify when we get on trend and analyze only those data. Final point, those data which cannot be corrected, Duong says that's due to skin effect. My translation of that is that's dominated by fracture fluid cleanup in this well. And those points definitely don't follow the trend line and certainly shouldn't be included in those data that we use to identify the parameters in our decline models. All right, what I want to do in the time that remains is show you several examples of data. I have two examples from the Barnett Shale to show you some gas well examples. I have two wells from the Bakken in North Dakota to show you examples of production histories from oil wells. All right, first this well from the Barnett Shale. You can see the well identifier here. If you want to look up and analyze these data for yourself on your favorite software. Here's what the data look like. This is the conventional semi-log plot of rate versus time. Now, in looking at these data, I'm hard-pressed to say that I can tell what flow regimes we might have here on this semi-log plot of data. All I can say is the shape of the curve is hyperbolic, so it does appear that we are dealing with this situation with hyperbolic decline. But we need to identify flow regimes before we draw any more conclusions. So here is a log-log plot of rate. This rate has been normalized by dividing by the maximum observed rate in history. That's not necessary. You can do that if you wish. It's been done here. And you see two different kinds of symbols here. You see some open blue circles. These points, this is a plot of rate versus actual time. Black dots, this is a plot of rate versus material balance time for this well. All right. In both cases, notice that the data eventually fall on a line which can be, or fall in a trend which can be fit very well by a straight line with a slope of -1/2. That's true with the material balance time plot. That's true with the real-time plot. So what flow regimes do we see in this particular case? Well, the only thing that we see is transient linear flow. And we can find how long that seems to have lasted on our actual time scale. We have transient linear flow in this case for 4,500 days. That's well over 10 years of transient linear flow in the history of this well, and no signs of any data influenced by boundaries. All right, having identified the flow regime that we have, this gives us a lot of insight into what we might do in modeling to match these data. Now, what I show here is the more commonly used semi-log plot of rate versus time. Now, all the data, except for the very earliest few data points, are in the trend which identifies transient linear flow. So we fit almost all the data with a single Arps decline model. Notice the B value. It's essentially 2.0. You know, there's enough scatter in the data. We don't get exactly that, but the fit is essentially 2.0. A slope of a B value of 2.0 is exactly what theory tells us to expect for transient linear flow. That corresponds to a -1/2 slope on our log-log plot. And we see that we can fit all these data very well with this Arps B of essentially 2. And so the parameters that you see here, this just comes from the particular software that we use to analyze these data. All right, if we make the assumption at this point that this transient linear flow trend that we see here is going to last for the entire life of the well, then we could just use these parameters from the Arps model fit for these data and use that to forecast production for the life of the well. If we were to do that for this well, we would estimate that the ultimate recovery for the well is about 3.4 billion cubic feet. But that's not really the right answer. The problem is that we can't expect these early transient flow regimes to last for the full life of the well. In fact, the odds are overwhelming that they will not. So what do we do about that? Well, this is not new. Most in the industry have been using a modified version of the Arps decline model and switching from the Arps B factor that fit the earliest data to another decline model later at some pre-selected decline rate. And that's what we've done here. We've switched from the Arps model. We attempted to switch when the decline rate reached 5% per year. Unfortunately, at the end of the data, the decline rate was already less than 5% per year, so we just switched at the end of the data to another Arps model, an Arps model for boundary-dominated flow. Now, one difference between what I prefer to do in practice and what is commonly done, I prefer to switch to an Arps model with a B factor appropriate for the kind of reservoir fluid and reservoir type that we're dealing with. And this is a gas reservoir, as we noted earlier. For a gas reservoir with modest pressure drawdown, Mike Fetkovich found in a classic paper on state-of-the-art decline curve analysis published in the late 1990s, we should expect a B value of 0.4 once we get into the boundary-dominated flow regime. So this forecast switches to a boundary-dominated flow model at this decline rate, and here's the forecast. Now, did this really make any difference? The EUR from this forecast is 3.12 BCF. From this forecast, 3.4 BCF. That's about a 10% difference. Some would say if we're within 10%, it really doesn't matter. But I think in this case it does. First, it's a matter of principle. You don't know what kind of difference in forecast you're going to have until you do it, taking into account the different flow regimes. Secondly, this is EUR. A lot of that EUR has already been produced. We also ought to focus on what are the remaining hydrocarbons yet to be produced. And the difference in the two forecasts there is considerably more than 10%. All right, let's look at another example from the Barnett Shale. Again, we have the well identifier here. Here are the data from this well, semi-log plot of rate versus time. Can we see flow regimes here? Well, I can't. All I can say is the shape is like a hyperbola, so this is a hyperbolic decline. A couple of downtime periods in the history here. How should we forecast in this case? Well, let's identify flow regimes and see. Here's our rate versus actual time and rate versus material balance time plot. Here's rate versus actual time. More important is this rate versus material balance time plot. Notice here that we see the data are fit very well after earliest times with a straight line with a slope of -1/2. That's transient linear flow. And then after a transition period, the later data begin to fall in a straight line with a slope of -1. That's boundary dominated flow. So we have both transient and boundary dominated flow regimes in this particular example. Okay, how can we then forecast? Well, we don't need to worry about using any information from the early transient flow regime in our forecasting. We'll just fit our data from the boundary dominated flow regime in this case. So notice I didn't make any attempt here. This is the forecast with this boundary dominated flow model. Notice I didn't make any attempt to fit the early data. We could have done that with a different model. The point is we don't need to. These data, starting at from the diagnostic plot we saw boundary dominated flow beginning, these are the data that we need to fit and forecast. And so we get just this single answer here, 1.8 BCF. And incidentally, the best fitting B value for the data in boundary dominated flow is 0.5. And Fetkovich told us that for a gas flow over the big drawdown, a B of 0.5 is an expected number. So we can have confidence in this forecast, barring some sort of operational difficulties later in the life of this well. All right, let's look at Bakken well. Here's the production history. Once again, we see a hyperbolic decline. There's a production discontinuity which lasts for a better part of 100 days. We really need a diagnostic plot to find out what flow regimes we have, and we're going to need this information for proper forecasting. So here again, here's the rate versus actual time with the open blue circles, rate versus material balance time, which is the more definitive of the plots, particularly when we're looking for the influence of boundaries and boundary dominated flow, but we don't see any influence of boundaries in this particular example. All these data are in transient linear flow. And this lasts up to something like 2,000 days. We're still in that flow regime. All right, let's forecast. Now, the transient data are fit very well by a B of almost 2, verifying the transient linear flow. Our production forecast, assuming that we remain in transient linear flow down to an economic limit rate, that gives us an EUR of 550,000 barrels. That's probably not right. And the problem is we should expect eventually a transition to boundary dominated flow. So here's what I believe is a better forecast. In this case, we switched from the early fit with a B of 2 to a fit during boundary dominated flow. We switched when the decline rate reached 5% per year, and the B value that we used for forecasting after that switch was 0.3. Now, where does that number come from? That's Fetkovich's recommendation for the B value for a well in boundary dominated flow for a solution gas dry reservoir. And so I believe this is the more defensible forecast. EUR 481,000 barrels versus 550. That's a significant difference. And again, the difference in the EURs really understates the difference in these two forecasts, because much of that EUR has already been produced. So the difference in remaining reserves is pretty substantial in this case, depending on how we forecast. But we can do this rationally with this identification of flow regimes, and then taking into account that eventually the odds are overwhelming that we will switch to a boundary-dominated flow regime. One more Bakken well. Here's the history. Hyperbolic looking decline. Flow regimes, not obvious. In this case, it looks like we do have some production instabilities at late times. Let's look at our log-log diagnostic plots again, rate versus actual time. And here we see we can fit the early data pretty well with a straight line, with a slope of -1/2. Then we get a deviation from that line, and here's our operational upset. The data really begin to scatter. Here's a plot of the data versus material balance time. Looks like after some early time, probably caused by choke backflow, we eventually do see the linear flow trend. We see the beginning influence of reservoir boundaries, and here later in time, perhaps a unit slope line, indicating that perhaps we have reached boundary-dominated flow. Now, we need to be careful in using material balance time and calculating material balance time whenever we have operational upsets like this. These sort of data can incorrectly tend to fall on a unit slope line. Unfortunately, in gas well, the operational upset will be unloading the wellbore, or loading of the wellbore and then unloading it. In this oil well, I don't know exactly what the problem is, but anyhow, there is an operational upset. Nevertheless, our best forecast that we can make with these data, I'm going to exclude those data during that late production instability and simply fit only the data that appear to be in boundary-dominated flow. In other words, I'm not going to worry about trying to fit the early data. Doesn't matter. That flow regime is over. We're in this flow regime now. In this case, we match these data with a B of 0.223, which is not unreasonable for a solution gas drive oil reservoir. So this is the basis for our forecast. And we forecast an ultimate recovery of about 300,000 barrels. So to summarize quickly and to leave a few minutes for questions, I note that to ensure more accurate production forecasts, my recommendations are, very importantly, first final flow regimes in the history of the well. If you see more than one flow regime, if you see a final flow regime which indicates boundary-dominated flow, fit that final flow regime. That will appear in the most recent history. And then once you fit, you can forecast. If you're in boundary-dominated flow in the historical data, then just select the most appropriate B value that fits that flow. If you have not reached boundary-dominated flow, if the diagnostic plot shows you're still in transient flow, then identify the end of that flow regime and select what you believe to be an appropriate final B value. You know, I've already said, based on Fetkovich's recommendations, for a gas well, a B in the 0.4 to 0.5 range is likely to be appropriate. For a solution gas drive oil reservoir, a B in the range of 0.3 is likely to be a value. Many analysts are more conservative than this and will choose a B of 0 for that final flow segment. I can't argue with conservatism, but I will say that in my opinion, I don't think it's necessary. use a final B of 0. I think we can have a higher B and with good conscience report a somewhat larger value for remaining production. And then finally, we need to find and use software which helps us do the kinds of things that I've been talking about here quickly and accurately. We certainly need to be able to prepare log-log diagnostic plots, for example, in order to go through the workflow that I've been outlining. So this concludes the lecture part of my presentation on identifying flow regimes, and I appreciate your attention. And as time permits, I'll be happy to try to answer any questions that you might have.
Thank you, Dr. Lee. I want to remind all our participants today that they are muted, so to post questions, they can use the question box there on the webinar dashboard. All our participants will receive a follow-up email to the webinar this afternoon, and you'll have a link to the recording of this webinar that you can watch on demand or you can share with your colleagues. The email will also include a link to register for Dr. Lee's two-day class. We're having it both in January and in May in Houston on this topic, and we'll ask for an evaluation. We're starting to get some questions, and I won't identify those of you who are asking the questions, so your anonymity is protected. So here's the first question. What about heavy oil flow as seen in they're coming in quickly, in horizontal wells? Heavy oil flow in horizontal wells, Dr. Lee.
Heavy oil flow should be analyzable using these same techniques. However, I want to be sure we're talking about horizontal wells with multiple fractures. If we are, the same sorts of techniques should be appropriate, so I don't have any reason to suggest any modifications in these procedures for that situation. You'll know whether or not it's going to work if you'll prepare the same diagnostic plots that I've suggested in this lecture. And hopefully you will see at least a early transient flow regime, and you may see a later boundary dominated flow regime. And then you can proceed exactly like we've done here.
Thank you. Next question, can you touch on how to select the appropriate time to switch to the boundary dominated flow when only transient linear flow is seen in the data?
That's the question as far as I'm concerned. Notice that I said in my examples where we had only transient flow, I said we had chosen to switch at a decline rate of 5%. But what's the basis for that? That's the question, and the answer is it's really a difficult problem to solve. Preferably, we will have other wells which are further along in their production history in the same general area of the play that we're working in. And in these wells that are further along, we can identify the time at which we finally got into boundary dominated flow. And we can do this, again, aided by the diagnostic plots that I've outlined, so we can see when the boundary dominated flow regime began. And once we've fitted the data with an Arps model or our favorite model of some other kind, we can determine what the decline rate was at the time that we got to boundary dominated flow. So I think actual field experience is the best way. However, the answer, as the questioner probably knows, is not necessarily that simple. We may have a range of apparent decline rates, and in that case, we probably would have to go with some kind of median value based on what we've seen. But let's suppose we're in a situation where we have only fairly short production histories, and we don't have good analogs. So what do we do then? The best work that I've seen here is based on running some example cases with a reservoir simulator. And in this reservoir simulation work, look at a range of different possible permeabilities in the formation of interest, look at a range of different fracture spacings, and look at a range of different fracture lengths. And I think you'll find that those three parameters will really control what the decline rate is once you get to boundary dominated flow. So a sequence of numerical experiments may be a good thing to do, maybe even in addition to trying to determine from analog production histories what this minimum decline rate is.
Thank you. Can you please elaborate on using Arps decline in water-flooded reservoirs?
I am pretty skeptical about using Arps or any other decline model in water-flooded reservoirs. Here's my concern. The decline rate in a water-flooded reservoir is going to be closely related to the water injection rate. So if you can insist that you're looking at data in which the injection rate has been maintained in a consistent way, and that you believe it will be maintained in that way in the future, then I think decline analysis has its place. But if the injection rate is not maintained, let's say constant, I really question use of the Arps model or any other decline model in that situation. So do it if you must, if that's the only tool available, but be very cautious about the results that you claim from that analysis.
Thank you. So I want to remind our viewers today, as we're nearing the end of our time commitment, that you will receive an email with follow-up, a link to a recording of this webinar. Thanks for sharing this with us, Dr. Lee. You'll have information about the classes that you're offering on this topic, forecasting for low permeability reservoirs. They'll be offered in Houston in June and May, and also we'll ask for some feedback on this webinar. So that's it for today. Thanks for everyone's time. Goodbye.
Goodbye.